Hello viewers, this is Bharat, a third year BTech Engineering Physics student at IIT Roorkee. Today I'll be performing the experiment Potentiometric Error Detector. First of all, let me talk about the objective of the experiment and give a brief overview about the experiment. Our objective is to delve into the performance characteristics of an angular position error detector employing two potentiometers. Potentiometric error detection constitutes a pivotal aspect within feedback control systems where the output variable is meticulously compared with the command or reference input. This comparison is instrumental in ensuring precise control over various mechanisms, particularly in position control systems where the potentiometers play a central role. In our study, we will explore the intricacies of this error detection methodology, examining its effectiveness, limitations, and potential applications. By scrutinizing the performance characteristics, we aim to glean valuable insights that can inform the design and optimization of control systems in diverse engineering domains. Through comprehensive analysis and experimentation, we aspire to contribute to the advancement of control theory and its practical implementation, fostering innovation and efficiency in technological endeavors. Equipment description, signal sources. DC. We will be utilizing a DC signal source with a regulated output of 1 volt. This source ensures stability and precision in our measurements. Our AC signal source operates at a frequency of 400 Hz with an amplitude of 1.2 volts peak to peak. This alternating current facilitates dynamic analysis and testing. Second, measurement equipment. A 3/2 digital voltmeter (DVM) is conveniently available on the panel for the accurate measurement of DC signals. This instrument provides reliable readings and aiding in the assessment of system performance. For AC measurements, an external cathode ray oscilloscope will be necessary. The CRO enables visualization and analysis of the alternating signals, offering insights into their waveform characteristics and behavior. Error detector. The error detection mechanism comprises two zero potentiometers meticulously calibrated to ensure accuracy down to the finest resolution. These potentiometers play a crucial role in detecting and quantifying angular position errors within the system. Demodulator. To facilitate AC operation, a dedicated demodulator is integrated into the setup. This component extracts the modulated signal, enabling precise analysis and interpretation of the AC responses. Power supply. A reliable power supply is included to ensure uninterrupted operation of the experimental setup. This power source provides the necessary energy to drive the components and maintain consistent performance throughout the testing process. Here is the photo of the experimental setup with all the connections made. Now I will be telling about the methodology for DC excitation mode. First of all, begin by setting the excitation switch to DC mode to initiate the experiment under direct current conditions. Now, second, we will fix the position of the port 2. Maintain port 2 at a constant position θ2 throughout the experiment, and we will be avoiding any adjustment to this potentiometer to maintain consistency. The third step, incremental adjustment of port 1. We will be adjusting the port 1 in incremental steps of 20 degree, pausing at 10 degree intervals whenever there is a sudden change in voltage output. This step ensures accurate data collection. Fourth step, recording the data. We will be recording the angular position θ1 of port 1 and corresponding output voltage V0 using the digital voltmeter DVM available on the panel. This recorded data will serve as the basis for analysis. The fifth step, we will be plotting V0 versus θ1. Sixth step, analysis. We will be observing the plotted graph to assess the linearity and range of the system under investigation. We will be analyzing the relationship between the input angular position and the output voltage to derive insights into the performance characteristics. Then we will be repeating the different port 2 position. The entire process will be repeated for different positions of port 2 while maintaining the same experimental conditions. This step enables comprehensive analysis across various configurations and settings. Then we will be interpreting the data. Here, we will be fixing the position of port 2 at 180 degrees. Then we will be changing the position of port 1 We'll be adjusting the position of port 1 at 10 degrees and we'll take the observations. Now, I will be telling the methodology for AC excitation mode. First of all, measurement of carrier signal. I begin by displaying the carrier waveform on the cathode ray oscilloscope CRO and measure its amplitude and frequency using the CRO's built-in measurement tools. Second, switching excitation to AC. Next, I switch the excitation source to AC mode to initiate the experiment under alternating current conditions, ensuring proper calibration and synchronization with the AC signal source. Third, observation of output voltage V0. Using the CRO, I observe the output voltage V0 while slowly adjusting either port 1 or port 2, monitoring the changes in V0 in response to the adjustments made to the potentiometers. Recording and plotting V0. I record the peak to peak or RMS value of V0 as a function of the angular position θ of the adjusted potentiometer and plot the recorded data to visualize the relationship between the input angle and the output voltage amplitude. Fifth point, connection to balanced demodulator. I then connect the output voltage V0 to the input of the balanced demodulator, ensuring proper configuration and alignment of the demodulator for accurate signal processing. Sixth, recording V0 EM. I record the output voltage V0 EM from the balanced demodulator as a function of the angular position θ of the adjusted potentiometer. This data provides insights into the demodulated signal characteristics and the modulation efficiency. Then we will analyze and interpret the data accordingly. Here we are performing the experiment in AC excitation mode. Here is the observation table which I made after completing the experiment. The plot error versus output with AC excitation will look like as shown here. There are multiple applications which I will be discussing now. First of all, in robotics for precise position feedback. Second, industrial automation for accurate positioning in CNC machines. Third, in aerospace for navigation and control. Fourth, in automotive for vehicle control systems. Fifth, in medical devices as surgical robotics and patient positioning. Sixth, renewable energy for optimal alignment in wind turbines and solar tracking systems. Seventh, laboratory instruments for the precision measurements. Eighth, consumer electronics as the user interface control, integrated into digital cameras and gaming consoles for precise user interface control, enhancing user experience and device functionality in consumer electronics product. At last, thanks for watching. Hope you have a good day.